Okay, welcome to this final part of lecture 2. What I wanted to do is wrap this up with an example that all these methods that are seemingly quite complicated, which I think now you should be able to comprehend quite well if you read the papers, but they seem kind of complicated and it's a bit hard to see that most of them, all of them just talk about regular group convolutions, but with kernels expanded in a steerable basis. And this connection, I think it's nice because then you can rely on this intuition that group convolutions are all you need, and what is essentially being done is just template matching and generated higher dimensional feature maps. And this intuition can help you in designing your neural networks. So what I want to do, I want to start off with regular group convolution neural network and then transform them into a steerable group convolution, which turns out in this special case when I'm going to use the Fourier transform based on complex irreducible representation of SO2 is going to boil down in converting a regular group convolutional neural network into a harmonic network, a deep translation and rotation equivariance neural network. Okay, so let's revisit what we had so far. The regular group convolution setting generates these high dimensional feature maps, and the steerable case generates these feature fields where each vector represents, in a way, a signal over the subgroup H, which is made explicit with this visualization or animation, right? This vector could contain the Fourier coefficients, which can be translated to an actual signal on the subgroup H. Okay, so when it comes to these steerable group convolutions, I just mentioned that people have worked this out for us and there's convenient libraries to turn this into this. But actually what we learned theory-wise is mostly this Fourier transform and the regular group convolutions, but we haven't really seen how to actually solve this kernel constraint. So what we're going to do in this lecture, we're going to rely on the knowns that we have. So what do we know? We know the group convolution operator K. We know what this Fourier transform looks like, so we can use that actually these ingredients to derive what this steerable kernel looks like. Because applying this mapping, we could do it via this route, but what if we were to do this directly? That means that we're implicitly doing something like an inverse Fourier transform, then a group convolution, and then again a Fourier transformation. So what we're going to do is just compute this and see what comes out. Okay, so this is what we want to compute. We want to compute the steerable convolution operator defined by an inverse Fourier transform followed by a group convolution followed by a forward Fourier transform. So I'm going to use this color coding to keep it a little bit organized because it is a bit messy, I must say, a lot of terms. So I recommend you to take your time also afterwards to look at the slides and go over these steps, maybe do them yourself as well. Okay, now the idea is as follows. So let's expand this forward Fourier transform, right? So that's if I have a signal on the group H, then I can find the Fourier coefficients by just projecting the signal onto my basis, which in this case with SO2, with complex irreps, these are the complex irreducible representations of the 2D rotation group. So I'm just integrating my function multiplied with this irreducible representation. So this is the forward Fourier transform. I'm just fill it in over here. That's the blue part. Now, the green part is an inverse Fourier transform, which turns this feature field into a regular group feature map, and I apply a group convolution on it. And that generates a signal on position rotation space, right, on the group SE2. And that's the thing I'm going to take a pointwise Fourier transform of. So now let's fill in the group convolution and the inverse Fourier transform. Okay, so we know the group convolution looks like this. So we have a transformation of the kernel, right? We transform the spatial part and the angular part, integrated with our underlying signal over the entire group dx d theta. Okay, so that's indicated in red. And in green, we have this inverse pointwise Fourier transform, illustrated as follows, right? If I have a vector of Fourier coefficient, the inverse Fourier transform turns this into a signal on H by simply multiplying each coefficient with the corresponding inverse basis function. Okay, and that's the term that you see over here. Yeah, so this is all we need to compute, and that's peanuts, right? Of course, it's a bit complicated, but we can rewrite it a little bit. Maybe that's really the main step here, is to turn this, to reshuffle it such that we have this regular convolution form. So we have the integral over R2 with some kernel and the underlying signal. And that's a bit more becoming more clear over here. So what we're looking at is really already the form of the convolution that we're looking at, because this thing eventually we integrate over S1, so d theta prime, and what is left is a kernel, that depends on this relative position only. So we already see that this steerable convolution is going to be of this type, where K is a convolution kernel that maps an input feature field, a feature vector, so f hat L was a feature vector of dimensions in, to, it maps it to a feature field of dimension d out. So that has to do with how do you specify the input and output feature type. And this kernel, as we see, is really defined as such. I have to compute these two integrals, and that's what we're going to do next. But before we do that, I have to get rid of this typo. This L shouldn't be there. So what's happening here, this sum over L is really like the row vector multiplication, right? So I have a kernel that has for every input-output pair some value, and I do this matrix vector multiplication. That's so we row sum over the rows in K and over the columns in F. Okay, so we just need to compute these integrals of some regular group convolution kernel. And we haven't specified yet how did we parameterize this kernel. But since we're already talking, we see a lot of S1s over here, so it is already an indication that it's going to be much more convenient if we work with a steerable basis. So recall that we can basically express any convolution kernel in a steerable basis if we use enough harmonics, enough frequencies. So that is a sensible choice for a kernel, right? So we parameterize the spatial part with spherical harmonics, and we let these weights depend on the radius as before, but now also on this theta, right? Because this is a three-dimensional kernel, and the spherical harmonics, they only do a spatial, like the in-plane parameterization of this kernel. So we have weights that also still depend on this theta. Okay, and we do this, of course, because once this is done, then such kernels are simply rotated, and we need this rotation. These kernels are simply rotated by a multiplication with this complex exponential. Okay, so let's stick to this parameterization and fill it in our expression over there. So we're going to fill this in. So this is what our kernel quite explicitly looks like. We fill it in over here, and that means we have to compute this integral. And initially this doesn't make it look much easier, but it is going to be much easier, because now we have all these complex exponentials. We got rid of this rotation part over here simply by multiplying it with this complex exponential, which I can merge with these other terms over there. So let's reshuffle a bit. So I moved this e to the power minus a j over there. So we have this exponential depending on theta. So I'm going to merge it with that one over there. So that gives me this. All right, and now there's another interesting to observe over here is that this thing, so we have here, we want to get rid of this term, right? So we have to compute this integral over theta prime of this function that depends on theta prime, multiplied with this, representation of Fourier basis function. So what we're looking at here is actually a Fourier transform coupled with the shift theorem, because we know that if we want to evaluate the shift, we could also first do a Fourier transform and then do the shift in the Fourier domain via the representation of the group. And this is actually something that maybe helps if you try this out at home, but you can also just believe me on this. We can do a change of variables, because now the Fourier transform, forward Fourier transform, was actually defined with a plus over here, and that's what we've been using, but we could do a change of variables, of course. And that swaps things around here and there, and that generates this conjugate sign over here. But the main point is we can use these tricks from Fourier theory to move this shift and recognize this as a Fourier transform to write in such a form. So what we're dealing with is W. You take the Fourier transform as this function W, we indicate it with a hat. Okay, and now we're almost there, because now we have these Fourier coefficients, or this kernel, which represents a bunch of Fourier coefficients that depend only on the distance, the relative distance, and this is multiplied with this bunch of complex exponentials. So what we can do, we need to integrate over theta, right? So let's move everything that depends on theta, on outside of this integral and keep everything else inside. And that's like this. So this all doesn't depend on theta, and I want to compute is this integral over these complex exponentials. And these L, J, capital J, and lowercase j are all just frequency indices, right? So they're integers, which tells me that I'm really just integrating over rings, and that should always evaluate to 0 unless these things add up to 0, because then I'm just integrating over 1 over my ring. But otherwise a sinus and a cosine, yeah, it always integrates to 0 on this interval from 0 to 2 pi. So this simplifies things a lot. So this actually, I can get rid of this thing because it's almost times 0, and when it's not 0, it's just 2 pi, and we have some factor in front of it. And actually in this step, I sort of absorb this factor into these weights. It shouldn't matter too much, it's just a constant. Okay, so now I've managed to reduce this expression for the kernel all the way to, again, a steerable basis function, where this steerable basis function only consists of spherical or circular harmonics with frequency j, which corresponds to the cases where capital J equals J minus L. And this is in the harmonic network paper referred to as the equivariance condition, and basically tells us that we have this input index L, which corresponds to the frequencies in the input, and the frequencies in the output J. And suppose I have a scalar field as input, so L is 0, so a type 0 irreducible representation field trivially transforms, and I want to generate a response with frequency 1 or 2 or 3 with frequency J. Then it means that capital J should be J minus 0, should be just the frequency whatever I want. And so by this rule, I can alternate between different types of frequencies, and I'm going to visualize it by taking a look at the paper of the harmonic networks. But the point here is the steerable convolution kernel is really just another kernel expanded in a steerable basis, and with this we can obviously detect very interesting patterns, and the kind of basis functions that we choose determine what kind of output frequencies I will end up with. Or put differently, if I want to only see particular output frequencies, then I have to pick the J's in such a way that, we have the output frequency minus the input frequency, and that's a J that I am allowed to pick. So we already had a regular group convolution kernels, which really didn't have any particular constraints on them. And then we have the steerable group convolutions, which were really just spatial convolutions, but with kernels that had some constraint on it. And we just saw that whenever we parameterize our convolution kernels, which are matrix valued in such a way by expanding it in this circular harmonic basis, then we're good. And this also tells us that we can go back and forth this regular convolution kernel and our steerable convolution kernel via this Fourier transform. So this really shows that also these steerable group convolution kernels are really special cases or instances of regular group convolutions. And so what I did in this whole derivation, I assumed we have an input specification of the maximum frequency L max, let's say, an output specification, and then I can pick the frequencies J's such that this equivariance condition holds. And then my kernel is really expanded in this circular harmonics basis. And so this condition J is J minus L is really the equivariance condition of the harmonic network paper. And I think now is a good time that we have a quick look at this particular paper. Okay, so this is the paper which I've been talking about, harmonic networks, deep translation and rotation equivariance. And we just put this in light of the regular group convolution framework, which isn't directly observable by just checking out the paper. But now that we've covered all this stuff about steerable group convolutions, you should be very much capable in reading this and putting this in context. So yeah, it starts off, of course, by saying, okay, what they're doing is they expand the kernels in a steerable basis. Okay, we've seen these basis functions before. Okay, it talks about this equivariance condition of the feature maps themselves. Let's see what else. Okay, so the kernel, the weights, so this is really the kernel is parameterized in polar coordinates, so that's something that we did. And then this is actually the steerability condition that we saw before, like that is close to how Freeman et al. Specified this. It's like we can either convolve a rotated feature map, or we can first convolve with our basis functions and then convolve afterward by multiplying with our complex representations. And that's illustrated in this figure over here. But I want to move on actually to this figure. This figure specifies this equivariance condition. Maybe let's look it up. That's summarized in this part. It's like if I have a feature map, a feature map that transforms via a frequency M1, and I'm convolving it with something with the filter based on frequency M2, then the output feature map is something that transforms via the frequency M1 plus M2. And in the complex case, we can talk about positive and negative frequencies. So that allows us to move between different types of fields. So the input is, for example, only transforming by type 0. Right? It's just a scalar value, the real value, the scalar value that doesn't transform. But then if I filter it again with an isotropic filter, maybe here, type 0, then I'm able to pick up isotropic patterns, right? So the feature maps generated by M0 filters are still of type 0. If I then convolve it with a frequency 1 filter, so let's say positive frequency 1, like this, then I generate actually feature values that transform with frequency 1. Okay, so that's these type of feature maps and so on. And so we can create these higher order frequency or directional responses in our feature maps. And then given such a feature field, which involves frequency 0, frequency 1, frequency 2, and I want to generate again a scalar field, then you have to convolve the first type with a filter of type 0, the first frequency with a filter circular harmonic with frequency -1, and this one with frequency -2, and then I add them up and that generates the input for this particular feature field. Okay, and then in this steerable framework, so this is a special instance where they work with complex irreducible representations. So they're not very explicit about that part of representation theory in this paper, but I mean, that's covered in different papers. So this is a special case of this steerable framework, and it's one of the first methods actually that does it in this way. And okay, so here they also say something about the nonlinearities, where they're saying that they use complex nonlinearities which act on the magnitudes of these feature maps, right? Because we just showed in the previous video that we can do whatever we want with the magnitudes, and then it's still steerable. Okay, so it's a super interesting paper, and you should definitely check it out. And I think what I like about this analysis that we just did is that this, at first sight, doesn't really look like a group convolution network, but we just saw that given such networks, there is an equivalent implementation via regular group convolutions. Okay, so let's get back to the overall presentation. I want to end with this statement because it connects to what we will see in lecture 3. So these steerable group convolutional networks are really just regular convolution with this complicated sum, or it's not really complicated, it's just multiplications, but only for allowable indices. So we have a field with output frequencies indexed with j. We have a field with input indices indexed with L, of our input frequencies indexed with L. And then we have a kernel that transitions from L to J. And we already saw if we want to have, for example, frequency 2 output and our input is frequency 0, then I'm allowed to have a frequency 2 filter, right? That's specified by this equivariance condition over here. And now we can remove this conditional sum by just summing over all j's when considering all possible weights or index combinations, but just setting most of them to 0, actually almost all of them to 0, and only a few of them survive. And once we do write it in this form, we recognize this Clebsch-Gordon tensor product structure that we will see a lot in these steerable neural networks papers. So these Clebsch-Gordon neural networks are really implementing a tensor product in which most of these multiplications will be 0, and the multiplications that won't be zeroed are parameterized by a weight that depends on the relative displacement or the relative distance. and the filters themselves or the convolutions themselves are obtained by evaluating the relative angles and expand that in spherical or circular harmonics. All right, and that's something that we will see in the next lecture when we talk about equivariant graph neural networks in 3D mostly.